Between 1900 and 2000, humanity invented powered flight, split the atom, landed on the moon, connected the world through the internet, and sequenced the human genome. 100 years of transformation. Now consider this. Between 2000 and 2020, we experienced roughly equivalent technological and social change in just 20 years. Smartphones went from non-existent to ubiquitous. Social media reshaped politics. AI progressed from chess-playing novelty to systems that generate art and code. Climate scientists confirmed that the rate of climate change now exceeds anything in the last 24,000 years, moving 10 to 100 times faster than historical norms. The pattern is unmistakable. Change isn't just happening, it's accelerating. The next 20 years, from 2025 to 2045, will compress even more transformation into an even shorter time frame. We're not approaching the future at a steady pace. We're careening toward multiple futures simultaneously, each arriving faster than our institutions and mental models can process. Before we start, a quick roll call. Write in the comments which part of this planet you're watching from, and then just listen and enjoy. The central question we're exploring tonight is this: how do we prepare for futures that arrive faster than our ability to plan for them? How do societies, communities, and individuals build resilience when the ground itself keeps shifting? And perhaps more importantly, what does innovation look like when we're not just solving today's problems, but anticipating problems that don't yet exist? By the end of this exploration, we'll understand why extreme futures isn't alarmism, but honest recognition of the velocity of change. We'll examine the specific systems already showing acceleration, from climate to technology to demographics. Century is slowing dramatically. The World Bank projects potential economic growth rates will fall to 30-year lows by 2030, driven partly by aging populations in developed nations and China. Meanwhile, Africa's population is projected to double by 2050, creating enormous youth cohorts that will either drive innovation or face unemployment at unprecedented scale. Geopolitical order is fragmenting. The post-World War II international system, already strained, is giving way to something new. Supply chains that seemed permanent are being redrawn. Energy systems are transitioning from fossil fuels to renewables, but not fast enough to avoid significant warming, and not slowly enough to give fossil fuel economies time for smooth transitions. These aren't separate crises. They're interconnected systems experiencing simultaneous stress. Climate change drives migration. Migration creates political instability. Political instability disrupts technology development and deployment. Technology disruption reshapes labor markets. Labor market changes affect demographics and family formation. Everything connects to everything else, and the feedback loops are intensifying. This is what makes our current moment distinct from previous eras of rapid change. The Industrial Revolution transformed society over roughly a century. The digital revolution unfolded over decades. What we're experiencing now is multiple revolutions converging within the span of a single generation. A person born in 2000 has already lived through the smartphone revolution, the social media transformation, the global financial crisis, a pandemic that reshaped work and education, and the emergence of AI capable of creative tasks previously considered uniquely human. They're only 25 years old. The term extreme futures can sound apocalyptic, but that's not what it means. Extreme doesn't necessarily mean catastrophic. It means rapid, disruptive, threshold crossing. It means the difference between weather and climate. But transistor scaling slows. Overall computational capacity continues growing through alternative architectures, cloud computing, and specialized AI chips. The result is that problems once considered computationally impossible become solvable, sometimes seemingly overnight. The World Bank's 2023 analysis projected that global economic growth rates will decline to 2.2% annually by 2030, down from over 3% in previous decades, representing what they called a lost decade for economic development. But that's the average. Within that average, some regions and sectors will experience explosive growth, while others stagnate or decline. Inequality isn't just about wealth distribution. It's about being positioned in growth sectors versus declining ones. Why does this matter? Because our institutions, mental models, and planning horizons were built for a different pace of change. Government budget cycles run 3 to 5 years. Corporate strategic planning typically spans 5 to 10 years. Infrastructure projects take decades from conception to completion. But technologies now move from laboratory to global deployment in years or even months. Climate tipping points, once theoretical future concerns, are becoming present realities. The human mind evolved to handle relatively stable environments with gradual changes. Our pattern recognition, our sense of normal, our comfort with routine. These served us well for most of human history, but they become liabilities in periods of rapid phase transition. We keep expecting tomorrow to resemble yesterday. We keep planning as if trends will continue. We keep being surprised when discontinuities occur. Yet here's the paradox. Humans are actually extraordinarily adaptable when circumstances demand it. Our ancestors survived ice ages, volcanic winters. Futures include renewed cooperation on global challenges, fragmentation into competing blocks, or various mixed outcomes. None of these futures is predetermined. They're possibility spaces, shaped by decisions and by chance, by policy and by innovation, by collective action and by individual choices compounded across billions of people. That's why preparation matters. Not because we can predict which future will arrive, but because we can build resilience that helps us navigate multiple possible futures. Resilience is often misunderstood. It's not about resisting change or maintaining the status quo. It's about flexibility, redundancy, and the capacity to reorganize under stress without collapsing entirely. A resilient system isn't necessarily strong in the sense of rigid. It's adaptable. It has multiple pathways to essential functions. It can absorb shocks and maintain core capabilities even when individual components fail. Think of a forest ecosystem. A mature forest contains tremendous diversity, species filling every niche, complex relationships between predators and prey, plants and pollinators, decomposers and soil builders. When fire sweeps through, the forest doesn't resist the fire. That's futile. Instead, it regrows. Some species sprout from roots that survived underground. Others, seeds, designed to germinate after fire, spring up in cleared ground. The specific configuration changes, but the forest as a system persists. Human systems can embody similar resilience, but we have to design for it deliberately. Modern civilization has optimized for efficiency, creating supply chains with minimal redundancy, infrastructure with single points of failure. Economic systems are coming. The challenge is preparing for them, despite not knowing precisely what they'll look like. That preparation happens at multiple scales. Individual level, learning skills that remain valuable across different scenarios. Community level, building local networks that can function when larger systems falter. Regional level, investing in infrastructure that can withstand various stresses. Global level, maintaining cooperation on challenges that transcend borders, even as other areas fragment. We're standing at a transition point. The pace of change we're experiencing now is unprecedented in modern history, but it's not unprecedented in human history. Our species has navigated transitions before. Migrations out of Africa, the agricultural revolution, the industrial revolution, each fundamentally transformed what it meant to be human. We're in another such transition now. The shape of the world 20 years from now, in 2045, will be as different from today as today is from 1985. Before widespread internet, before smartphones, before social media reshaped politics, before climate change became undeniable reality rather than abstract future threat. The difference is that we can see this transition coming. Not perfectly, not in detail, but in outline. We know the systems under stress. We know the technologies emerging. We know the demographic and environmental pressures building. That knowledge gives us something previous transitions lacked: the opportunity for intentional preparation rather than reactive scrambling. What that preparation looks like, what resilience means in practice, what innovations might help us navigate these extreme futures. Those are the questions we'll explore in the hours ahead. The path forward isn't clear, but the need to find it is undeniable. We're already living 1700s to late 1800s. Different regions industrialized at different times. People had decades to adapt, even if those decades were brutal for many. The transformation was revolutionary, but it was slow enough that institutions could eventually catch up. Labor laws, public health systems, compulsory education. Compare that to the digital revolution. The internet went from academic curiosity in the 1980s to essential infrastructure by the 2010s, about 30 years. Smartphones went from non-existent to ubiquitous in roughly 15 years, from the first iPhone in 2007 to market saturation by the early 2020s. Social media reshaped political discourse, retail economics, and human attention spans in less than a decade. The pace compressed dramatically. Now we're entering a period where multiple transformations of similar magnitude are happening simultaneously, and even faster. That's what makes the futures we're facing extreme. Not one big change, but cascading changes across climate, technology, demographics, geopolitics, and economics, all unfolding at once, all interacting with each other in unpredictable ways. Let's ground this in specifics. Climate systems are exhibiting nonlinear behavior that scientists categorize as tipping points. The Greenland ice sheet is melting faster than models predicted, even 5 years ago. Research published in 2023 showed mass loss accelerating to rates that could contribute a full meter of sea level rise by 2100 under high emission scenarios, with most of that rise occurring in the latter half of the century as melting accelerates. That's not a steady linear process where coastal cities can gradually build seawalls over decades. It's a process where the rate of change itself is increasing. Planning for 1 centimeter per year is manageable. Planning for 5 centimeters per year then 10, then 15 as feedback loops kick in. That's a different challenge entirely. Infrastructure built for one
compressed into decades rather than centuries.
Meanwhile, artificial intelligence is developing along its own accelerating curve. Current large language models can perform tasks that seemed impossible just 5 years ago. They write coherent prose, generate functional code, analyze complex data, and engage in reasoning that resembles human cognition in narrow domains. Whether this represents genuine intelligence or sophisticated pattern matching is philosophically debatable. But practically, it doesn't matter. The capabilities are real. AI research labs, both corporate and academic, openly discuss timelines for artificial general intelligence. Systems with human-level reasoning across broad domains, arriving somewhere between 2030 and 2045. Some researchers argue it could happen sooner. Others insist it's farther off or fundamentally impossible with current approaches. The uncertainty itself is significant. We might be 5 years from transformative AI, or 50, and we genuinely don't know which. What we do know is that narrow AI is already transforming labor markets. Automated systems handle customer service, data entry, basic legal research, medical image analysis, and increasingly complex manufacturing. Each year, tasks previously requiring human judgment become automatable. This doesn't always mean job elimination. Sometimes it means job transformation. Humans working alongside AI systems. But the pace of change is faster than workforce retraining can match. Biotechnology is accelerating similarly. CRISPR gene editing, discovered in 2012, moved from laboratory curiosity to clinical trials by 2020. In 2023, the FDA approved the first CRISPR-based treatment for sickle cell disease. We're now editing human genes therapeutically, something that was science fiction a decade ago.
The systems depend on more workers paying in than retirees drawing out. Real estate markets assume rising demand. Economic growth itself has historically correlated with population growth. When populations decline or age dramatically, those models break. Geopolitics is fracturing along new lines. The post-Cold War assumption of increasing integration, globalization, free trade, international institutions managing shared challenges, is giving way to great power competition, economic nationalism, and fragmented technology ecosystems. Supply chains are being redrawn based on geopolitical considerations rather than pure economic efficiency. The internet itself is fragmenting into distinct spheres with different rules and access. These aren't parallel developments, they're interacting systems. Climate change exacerbates migration, which increases political tension, which reduces international cooperation, which hampers climate action, creating a feedback loop.
AI development concentrates in a few countries and companies, creating technological inequality, which affects economic competitiveness, which drives further concentration. Demographic decline in some regions while others grow rapidly creates labor imbalances, which could be solved through migration, but political resistance to migration is rising. This is what makes our current moment extreme. We're not dealing with one challenge we can focus on solving. We're dealing with multiple, simultaneous pressures on interconnected systems, with changes happening faster than institutions can adapt, and with feedback loops that amplify rather than dampen disruptions. The speed matters more than most people realize. Human institutions have characteristic response times. Democracies operate on election cycles, typically 2 to 6 years. Corporations plan strategically over 3 to 10-year horizons. Infrastructure projects take decades. Education systems prepare students for careers that might last 40 years. These timeframes worked reasonably well when change was slower. But if transformative AI arrives in 10 years, education systems making decisions now are preparing students for a world that might not exist when
They're about the compounding effects of multiple rapid transitions happening simultaneously. A society could probably adapt to climate change alone, or AI transformation alone, or demographic shifts alone. Handling all three at once while geopolitics fragments and economic models struggle is exponentially more difficult. Yet this is precisely what we're facing between now and 2050. Not one extreme future, but extreme futures plural, each on its own accelerating trajectory, each interacting with the others in ways we can model, but not fully predict. The climate scenarios depend partly on technology deployment. Technology deployment depends partly on geopolitics. Geopolitics depends partly on economics. Economics depends partly on demographics. Everything connects. The question isn't whether these changes are coming. They're already here, already in motion. The question is whether we'll navigate them through deliberate preparation or reactive crisis management. Whether we'll maintain enough social cohesion and institutional capacity to implement solutions, or whether we'll fragment into competing groups unable to coordinate effectively. History provides both encouraging and discouraging precedents. Humans have navigated extreme transitions before. The Bronze Age collapse, the fall of Rome, the Black Death, the World Wars. Societies experienced catastrophic disruption and eventually rebuilt. But eventually often meant decades or centuries of reduced living standards, lost knowledge, and immense human suffering. Modern civilization, with its complexity and interdependence, is in some ways more fragile than simpler societies. We have less redundancy, more single points of failure, and vastly more people depending on systems functioning correctly. The extreme futures we're facing aren't predetermined. They're possibility spaces, probability clouds that collapse into specific outcomes based on choices and chance. A breakthrough in fusion energy or carbon capture could radically alter climate trajectories. A major AI safety failure or geopolitical conflict could set development back decades. Demographic patterns could shift. Preparation actually means in practice. Climate doesn't care about political cycles or economic convenience. It operates on physics, chemistry, and feedback loops that respond to greenhouse gas concentrations in the atmosphere, regardless of how we feel about it. Right now, in 2025, we're at approximately 1.2 degrees Celsius of warming above pre-industrial levels. The Paris Agreement aimed to limit warming to 1.5 degrees, with 2 degrees as an absolute maximum. We're on track to exceed both unless emissions drop dramatically and immediately. Current projections, based on existing policies and commitments, point toward 2.5 to 3 degrees of warming by 2100. That might sound modest, just a few degrees. But global average temperature is like body temperature. A fever of 2 degrees changes everything. A global temperature increase of 2 to 3 degrees reorganizes where rain falls, where crops can grow, which regions become uninhabitable, and how ocean currents and atmospheric circulation function. Let's walk through what different warming scenarios actually mean in practical terms. At 1.5 degrees, which we'll likely reach in the early 2030s, coral reefs experience mass bleaching events that kill 70 to 90% of reef systems. Arctic sea ice disappears almost completely during summer months. Extreme heat waves that occurred once per decade become once every few years. Regions already prone to drought experience longer, more severe dry periods. But food systems largely adapt. Mass migration is manageable. Coastal flooding increases but remains within adaptive capacity for wealthy nations. At 2 degrees, which current trajectories suggest we'll reach by mid-century, around 2050, the impacts scale non-linearly. It's not just 33% worse than 1.5 degrees, it's threshold crossing worse. Virtually all coral reefs die. The Amazon transitions towards savanna. Arctic permafrost melts at accelerating rates, releasing a 3-degree scenario, primarily from coastal flooding, agricultural collapse, and regions becoming physiologically uninhabitable. 300 million migrants is roughly the population of the United States. Imagine that entire population needing to relocate within a few decades. Where do they go? How do receiving regions absorb them? What political tensions emerge? This isn't abstract future speculation. Migration pressures are already building. The Syrian civil war, which contributed to European migration crises in the 2010s, was partly triggered by severe drought that displaced rural populations. That was in a world at 1 degree of warming. Scale the climate pressure up, and the migration pressure scales non-linearly. Coastal cities face existential decisions. Sea level rise under current emission trajectories could reach 0.5 to 1 metre by 2100, with some projections higher if ice sheet collapse accelerates. That might not sound dramatic, but it's not just about water level. It's about storm surge, king tides, and saltwater intrusion into freshwater supplies. Cities like Miami, Mumbai, Shanghai, Lagos and Bangkok face either massive infrastructure investment in barriers and pumping systems,
or managed retreat, abandoning low-lying areas. The Netherlands has centuries of experience managing water through dikes and barriers. They'll likely adapt, though at enormous cost. But the Netherlands is wealthy and has institutional capacity. Many vulnerable coastal cities are in developing nations without the resources for massive infrastructure projects. They'll face harder choices: protect valuable areas and abandon others, creating internal displacement and economic losses. Agricultural adaptation is possible, but difficult. Farmers can shift to heat-resistant crop varieties, adjust planting schedules, invest in irrigation, or relocate to regions with more favorable conditions. But these adaptations require capital, knowledge, and time. Subsistence farmers invest energy-intensive, requiring about 3 to 4 kilowatt hours per cubic meter. Renewable energy could power it, but that requires massive build-out of solar and wind capacity, plus storage. Atmospheric water harvesting, pulling moisture from air, works in humid regions, but is even more energy intensive than desalination. Wastewater recycling is more efficient. Singapore recycles virtually all wastewater, purifying it to drinking standards. California is expanding similar systems, but implementation requires infrastructure investment and public acceptance of drinking treated wastewater, which faces cultural resistance in many societies. Despite being scientifically safer than many natural water sources. The climate scenarios aren't just about temperature and precipitation. They're about ecosystem reorganization. Forests migrate toward poles as temperatures rise. But trees can't migrate faster than a few kilometers per decade, while climate zones are shifting tens of kilometers per decade in some regions. The mismatch means forests die faster than they can migrate, creating vast areas of dead and dying trees that become fire fuel. Wildfire seasons are lengthening and intensifying. The Western United States, Australia, Mediterranean Europe, and parts of South America are experiencing fires that exceed historical norms in frequency and severity. Firefighting is becoming year-round rather than seasonal. Smoke affects air quality across entire regions, with measurable health impacts. Insurance markets are pulling back from high-risk areas, leaving homeowners unable to get coverage. Extreme weather events are increasing in frequency and intensity. Hurricanes are getting wetter and possibly stronger. Atmospheric rivers, concentrated streams of moisture that can dump enormous rainfall in short periods, are becoming more common. Flooding affects regions that rarely experienced it historically. Infrastructure designed for 100-year flood events experiences those events every decade, or even more frequently. The challenge with adaptation is that it's local and specific. What works for coastal flooding in the Netherlands? This creates profound ethical and political questions. Who decides which places get protected and which get abandoned? How do you manage retreat from regions people have inhabited for generations? What obligations do wealthy nations that contributed most to historical emissions have toward poorer nations bearing the worst impacts? These aren't technical questions with engineering solutions. They're moral and political questions. that will define the next several decades. The climate futures aren't predetermined. Emissions trajectories could shift dramatically with rapid deployment of renewables, nuclear, carbon capture, and efficiency improvements. But even aggressive mitigation scenarios involve significant warming and adaptation requirements. The carbon already in the atmosphere commits us to decades of continued change. We're not choosing between climate change and no climate change. We're choosing between manageable change requiring substantial adaptation and extreme change requiring transformation of how and where billions of people live. Hope exists in unexpected places. Renewable energy costs have plummeted far faster than experts predicted. Solar and wind are now the cheapest sources of new electricity generation in most of the world. Battery storage costs are falling similarly. Electric vehicles are reaching price parity with combustion engines. The technological tools for deep decarbonization exist or are emerging rapidly. The question is deployment speed. Replacing global energy infrastructure takes decades, even under optimistic scenarios. Every year of delay locks in more warming and more adaptation requirements. But every fraction of a degree avoided makes adaptation easier and reduces threshold crossing risks. The difference between 2 and 3 degrees is immense. The difference between 1.5 and 2 degrees is significant. Every bit of warming avoided matters. Adaptation isn't defeat, it's realism. We will experience significant climate change regardless of mitigation efforts, because of emissions already released and inertia in both climate and economic systems. Preparing for those changes through investment can overcome quickly. Understanding which is which matters for preparing for extreme futures. Artificial intelligence dominates current technological discourse, and for good reason. The capabilities of large language models in 2025 would have seemed impossible 5 years ago. Systems like GPT-4 and its successors can write coherent prose, generate functional code, analyze complex datasets, and engage in reasoning that resembles human cognition in narrow domains. They're not intelligent in the general sense. They're sophisticated pattern-matching systems trained on vast amounts of data. But functionally, for many tasks, the distinction doesn't matter. Current AI systems excel at tasks involving pattern recognition, language processing, and generating outputs based on training data. They struggle with true reasoning, especially in novel situations where training data doesn't provide clear patterns. They hallucinate, generating plausible sounding but incorrect information. They lack genuine understanding of causality. But these limitations are narrowing as training methods improve and computational power increases. The timeline for artificial general intelligence, systems with human-level reasoning across broad domains, remains genuinely uncertain. Some AI researchers predict AGI could arrive as early as 2030. Others argue it's decades away, or fundamentally impossible with current approaches. The honest answer is that nobody knows. AI development has repeatedly surprised experts, both with unexpected breakthroughs and persistent limitations. What we can say with confidence is that narrow AI will continue transforming labour markets between now and 2045. Medical diagnosis is already being augmented by AI systems that analyse imaging and patient data. Legal research increasingly relies on AI-powered document analysis. Customer service is shifting to AI chatbots for routine inquiries. Software development is being assisted by AI code generation tools that can write boilerplate code or debug existing
manufacturing jobs, but created technology sector jobs. But eventually can mean decades, and during the transition, significant portions of the workforce struggle. By 2045, AI will likely be embedded in virtually every aspect of life in developed nations. Personal AI assistants managing schedules, finances, and communication. AI-powered healthcare, providing continuous monitoring and early intervention. AI-optimized transportation routing traffic and potentially driving vehicles. AI-generated entertainment, customized to individual preferences. The boundary between human and AI decision-making will blur in ways that raise profound questions about agency and autonomy. Biotechnology is accelerating similarly. CRISPR gene editing moved from laboratory discovery in 2012 to clinical trials by 2020 to FDA-approved therapies for sickle cell disease by 2023. The technology allows precise editing of genetic code, opening possibilities for treating genetic diseases, enhancing crops, and potentially even human enhancement. The ethics are complex and largely unresolved, but the technical capability is advancing rapidly. Synthetic biology takes this further, designing organisms from scratch or substantially rewriting existing genomes to produce desired outcomes. Bacteria engineered to produce insulin, spider silk proteins, or industrial chemicals. Yeast modified to generate pharmaceuticals. Algae designed to capture carbon dioxide more efficiently. The potential applications span medicine, manufacturing, agriculture, and environmental remediation. The risks scale with the capabilities. Engineered organisms released into ecosystems could have unforeseen consequences. Gain-of-function research on pathogens, intended to prepare for pandemics, could inadvertently create them. Gene drives that spread modified genes through wild populations could reshape ecosystems irreversibly. As the technology becomes cheaper and advancement, one with immense potential but facing fundamental physical challenges. Quantum computers leverage quantum mechanical effects to perform certain calculations exponentially faster than classical computers. Breaking current encryption, simulating molecular behavior for drug discovery, optimizing complex logistics. These applications could be transformative. But quantum computers are extraordinarily difficult to build and maintain,
They require temperatures near absolute zero. Quantum states are fragile and easily disrupted by environmental noise. Scaling from tens of qubits to millions of qubits, required for practical applications, faces massive engineering challenges. Current quantum computers can perform specific tasks that demonstrate quantum advantage, but they're not yet practically useful for most real-world problems. The timeline for practical quantum computing remains uncertain. Optimistic projections suggest useful systems by the 2030s. More conservative estimates push it to the 2040s or beyond. Some researchers question whether current approaches will ever scale to practical levels. Breakthroughs could accelerate progress dramatically, or fundamental barriers could stall development. Energy technology is advancing, but facing different constraints. Solar and wind power costs have plummeted over the past decade, making them the cheapest sources of new electricity generation in most regions. Battery storage costs are falling similarly, making intermittent renewable energy more viable. Electric vehicles are approaching price parity with combustion engines. The technical pieces for deep decarbonization exist. The challenge is deployment speed and scale. Replacing global energy infrastructure takes decades, even under optimistic scenarios. Grid modernization to handle distributed renewable generation requires massive investment. Manufacturing capacity for solar panels, wind turbines, and batteries needs to scale dramatically. And driven by reusable rockets, private investment, and renewed national interest. SpaceX's reusable Falcon 9 and developing Starship have dramatically reduced launch costs. Multiple nations and companies are planning lunar bases, Mars missions, and asteroid mining operations. The 2030s and 2040s could see substantial human presence beyond Earth orbit. But space remains difficult and expensive despite progress. Launching payloads to orbit still costs thousands of dollars per kilogram, even with reusability. Keeping humans alive beyond Earth requires complex life support systems. Radiation exposure in deep space poses health risks we don't fully understand. The timeline for Mars colonization, discussed in depth previously, depends on sustained commitment and solving numerous technical challenges. Nanotechnology, once hyped as transformational, has delivered incremental improvements rather than revolutionary changes. Nanoscale manufacturing improves materials and electronics gradually. Carbon nanotubes and graphene offer enhanced strength and conductivity, but haven't transformed industries at the scale predicted decades ago. Medical nanorobots remain largely theoretical. The lesson is that some technologies progress more slowly than early enthusiasm suggests. Brain-computer interfaces are advancing from medical applications toward consumer uses. Current systems help paralyzed patients control prosthetics or communicate through thought. Companies like Neuralink are working toward higher bandwidth interfaces that could eventually allow direct brain-to-computer data transfer. The technology raises profound questions about privacy, identity, and what it means to be human. By 2045, we might see early adopters using brain interfaces for enhanced memory, accelerated learning, or direct access to information. Or the technology might remain medical only due to safety concerns and societal resistance. The uncertainty reflects that some technologies face social and ethical barriers as significant as technical ones. The Internet of Things continues expanding, connecting billions of devices to networks,
leading to structural unemployment. The reality probably lies between these extremes. Some sectors will experience significant labor displacement. Others will see job transformation rather than elimination. New jobs will emerge in areas difficult to predict. The transition will be disruptive regardless, requiring substantial social adaptation and possibly new economic models. Why does technological change feel more extreme now than previous eras? Several factors converge. First, the pace has genuinely accelerated in some domains. Computing power, AI capabilities, gene sequencing costs, solar panel efficiency, all improving exponentially or near exponentially. Second, multiple technologies are advancing simultaneously and interacting. AI accelerates drug discovery. Biotech creates new materials. Quantum computers might optimize logistics and climate modeling. Third, global connectivity means technological changes spread faster than ever before. A breakthrough in one laboratory becomes available worldwide within years or months. Fourth, populations are more concentrated in cities and are more dependent on complex systems, making technological disruption more immediately visible and impactful. By 2040 to 2045, technology will look fundamentally different from today, in ways both predictable and surprising. Predictable includes continued AI advancement, deeper biotech capabilities, broader space access, more connected devices, and cleaner energy. Surprising includes breakthroughs we can't anticipate and failures of technologies we expect to succeed. The extreme technological futures we're facing aren't about any single invention. They're about the cumulative effect of dozens of advancing technologies, each transforming different aspects of life, all happening simultaneously within a few decades. That's about how a forest responds to wildfire. Individual trees burn, local ecosystems are destroyed. But the forest as a system persists because it has diversity. Some species sprout from roots that survive underground. Others, seeds designed to germinate after fire, colonize the cleared ground. Fungi networks in the soil maintain connections.
The specific configuration changes, but the forest regenerates. That's resilience, not resistance. Human systems can embody similar principles, but we have to design for them deliberately. Modern civilization has optimized for efficiency, creating supply chains with minimal redundancy, infrastructure with few alternative pathways, economic systems dependent on continuous growth and just-in-time delivery. Efficiency is valuable when conditions are stable. It becomes fragility when conditions shift rapidly. The pandemic demonstrated this vividly. Global supply chains, optimized to deliver goods with minimal warehousing, collapsed when a single variable changed: a virus spreading between countries. Suddenly, masks, ventilators, and basic medical supplies became scarce, despite the world having plenty of manufacturing capacity. The capacity existed in the wrong places, distributed to optimize for cost rather than robustness. Reshoring, nearshoring, and building inventory buffers reduces efficiency, but increases resilience. This efficiency-resilience trade-off appears everywhere. Centralized power grids are efficient, generating electricity at large plants and distributing through transmission networks. But they're vulnerable. A major storm, cyber attack, or equipment failure can black out entire regions. Distributed generation through rooftop solar, local wind, and battery storage is less efficient in pure cost terms, but far more resilient. If one node fails, others continue operating. Food systems face similar tensions. Industrial agriculture produces enormous yields through monoculture crops, specialized equipment, and global distribution networks. It's seawater and recycled wastewater purified to drinking standards. If any single source fails, others continue operating. This redundancy is expensive compared to relying on one cheap source, but it makes the system nearly failure-proof. Nature-based solutions represent resilience thinking applied to environmental challenges. Instead of fighting natural systems with hard engineering, work with them. Wetlands absorb floodwaters more effectively than concrete channels. Mangrove forests protect coastlines from storm surge better than seawalls. Urban forests reduce heat island effects and manage stormwater while providing biodiversity habitat. The Netherlands, a nation largely below sea level, has pioneered integrated approaches combining hard infrastructure with natural systems. They're creating room for the river projects that allow controlled flooding in designated areas rather than trying to contain every cubic meter of water behind dikes. They're building floating architecture that adapts to changing water levels rather than resisting them. These approaches acknowledge that you can't entirely control nature. You can only adapt intelligently to it. Material science is developing innovations that embody resilience at the molecular level. Self-healing concrete contains bacteria that remain dormant until cracks form, then activate to produce limestone that fills the gaps. Self-repairing plastics use embedded microcapsules that release healing agents when the material is damaged. These materials cost more initially, but potentially last far longer and require less maintenance, reducing life cycle costs while improving reliability. Carbon capture materials offer another avenue for resilience. Direct air capture technologies remove CO2 from the atmosphere, potentially allowing us to reduce greenhouse gas concentrations even if emissions aren't eliminated immediately. This provides a backup option, a way to correct course if emission reductions prove insufficient. The technology remains expensive and energy intensive, but costs are falling as scale increases and methods improve. Circular economy models represent systemic resilience thinking. Linear economies extract in circular models are buffered from some of these pressures. Energy transitions offer perhaps the clearest example of building resilient systems for extreme futures. Fossil fuel dependence creates multiple vulnerabilities. Resource depletion, price volatility, geopolitical instability, and climate damage from emissions. Transitioning to renewable energy addresses all these issues simultaneously, though it creates new challenges around intermittency and grid management. The cost curves for solar and wind have declined dramatically, falling roughly 90% for solar photovoltaics and 70% for wind power over the past decade. These technologies are now the cheapest sources of new electricity generation in most regions. Battery storage costs are following similar trajectories, making it increasingly feasible to store renewable energy generated during peak production times for use during peak demand. But resilient energy systems need more than just renewable generation. They need diverse sources so that cloudy, windless days don't cause blackouts. They need geographic distribution so that regional weather doesn't affect everything at once. They need storage at multiple scales, from small batteries in homes to grid-scale facilities. They need demand management that shifts consumption to match variable supply. And they need redundancy, backup capacity that sits idle most of the time, but activates during stress. Nuclear power remains controversial, but offers resilience benefits. Advanced reactor designs promise to be safer, generate less long-lived waste, and possibly even consume existing nuclear waste as fuel. Small modular reactors could be manufactured at scale and deployed in distributed patterns, rather than requiring massive centralized plants. Nuclear provides baseload power that doesn't depend on weather, complementing variable renewables. Fusion energy, if commercialized, would provide nearly unlimited clean energy. Multiple private companies are making progress toward demonstration plants in the 2030s, though commercial viability remains uncertain. Even delayed less land and water, while producing year-round harvests independent of outdoor climate. Lab-grown meat could eventually provide protein without the massive land, water, and emissions footprint of conventional livestock. These agricultural innovations won't replace traditional farming entirely, but they diversify food production systems. When traditional agriculture struggles with drought or extreme heat, controlled environment agriculture continues. When energy costs make vertical farming economically challenging, conventional farming provides alternatives. Diversity itself is resilience. Water systems need similar innovation. Desalination provides resilience in coastal regions, turning essentially unlimited seawater into fresh water. Costs have dropped substantially, and renewable energy can power desalination to eliminate the carbon emissions issue. Atmospheric water harvesting pulls moisture from air, working anywhere humidity exists. Wastewater recycling can reclaim virtually all water from human use, creating closed loops where every drop is used multiple times before any leaves the system. These technologies exist now, proven at various scales. The question is deployment speed and scale. Building resilient water infrastructure requires massive investment and time. Retrofitting existing systems is more challenging than building new. Political will and public acceptance take time to develop. But the alternative, continued dependence on rainfall patterns that are destabilizing, is increasingly risky. Infrastructure resilience extends beyond water and energy to transportation, communications, and built environments. Roads designed to withstand heavier flooding and more extreme temperature swings. Bridges built with materials that tolerate greater stress. Communications networks with mesh topology so that multiple paths exist between any 2 points. Buildings designed for passive survivability, maintaining livable conditions even during extended power outages. The challenge is that infrastructure lifespans measure in decades. Investing in community spaces, supporting local institutions, and fostering connections across different demographic groups. Education systems need resilience thinking. Instead of training students for specific jobs that might not exist in 10 years, teach adaptability, critical thinking, and learning how to learn. Emphasize understanding underlying principles over memorizing procedures. Develop comfort with uncertainty and change, rather than expecting stability and predictability. Healthcare systems are facing simultaneous pressures from aging populations, chronic disease burden, and potential pandemics. Resilient healthcare combines preventive medicine, reducing disease incidence, distributed care through telemedicine and home monitoring, surge capacity for emergencies, and redundant supply chains for critical drugs and equipment. Financial systems need resilience against shocks that cascade globally within hours. This might mean stricter capital requirements that buffer against losses, circuit breakers that halt trading during extreme volatility, or structural changes that reduce interconnections that transmit failures across institutions. None of these resilience strategies are simple or cheap. They require accepting higher costs, maintaining redundancy that seems wasteful during normal times, and planning for scenarios we hope never occur. But the alternative is systems optimized for conditions that no longer exist, vulnerable to disruptions that are increasingly frequent and severe. Efficiency works beautifully in stable environments. The extreme futures we're facing aren't stable. They're turbulent, unpredictable, and accelerating. Resilience is how we navigate that turbulence without collapsing. Memets exceed the capacity of conventional solutions. Innovation moves from incremental improvement to radical reimagining. Some of the technologies being developed and deployed to address extreme futures push at the edges of what's physically possible, ethically acceptable, and politically feasible. These aren't guaranteed successes. Many will fail. Some might create problems worse than the ones they solve.
Counteract the warming from doubled CO2 concentrations would cost perhaps tens of billions of dollars annually, orders of magnitude cheaper than deep decarbonization. Aircraft or high-altitude balloons could deliver the particles. The technology isn't particularly complex, but the risks and uncertainties are enormous. Reducing incoming sunlight doesn't remove CO2 from the atmosphere. It just masks one symptom of the problem, while ocean acidification and other CO2 effects continue. Regional climate patterns would shift unpredictably. Monsoons might weaken, affecting billions who depend on seasonal rains for agriculture. Once started, stopping suddenly would cause rapid temperature rebound, potentially faster than ecosystems could adapt to. And there's no global governance framework for deciding who controls the planet's thermostat. Despite these concerns, research continues because the alternatives might be worse. If climate impacts become catastrophic and emissions reductions prove insufficient, solar radiation management might become the least bad option. Multiple research programs are studying small-scale tests to better understand effects before any deployment decisions. The technology exists at the edge of possibility, ready to use if desperation demands it, but hopefully unnecessary if emission reductions succeed. Carbon dioxide removal takes a different approach. Pull greenhouse gases back out of the atmosphere. Trees do this naturally through photosynthesis, which is why reforestation and afforestation are often cited as climate solutions. But forests take decades to mature, require vast land areas, and can burn or be cleared, releasing captured carbon back to the atmosphere. Technological approaches offer alternatives with different trade-offs. Direct air capture uses chemical processes to extract CO2 from ambient air. The captured CO2 can be stored underground in geological formations or used industrially. Current facilities are expensive and energy-intensive, capturing CO2 at costs of several $100s per ton. But costs are declining as the technology scales and improves. If powered by renewable energy, direct air and distributing them at scale would be a massive industrial undertaking, with its own environmental impacts. Enhanced weathering applies similar principles on land, spreading crushed silicate rocks on agricultural fields. The rocks slowly dissolve, consuming atmospheric CO2 in chemical reactions. This is completely natural. It's how Earth's carbon cycle operates over geological time. But enhancing it artificially could remove gigatons of CO2 annually. The challenges are logistics and cost of processing and transporting enormous quantities of rock. These carbon removal technologies share a common limitation. Their energy
and resource intensive. Removing the trillion tons of CO2 humans have added to the atmosphere would require industrial operations at a scale humanity has never attempted. But every ton removed makes the climate problem slightly more manageable. Even if removal can't solve the problem alone, it could complement emission reductions and buy time for adaptation. Space-based solutions represent the outer edge of innovation. Solar power satellites would collect solar energy in space, where sunlight is constant and more intense than on Earth's surface, then beam it to ground stations as microwaves. The concept has been studied since the 1960s, but remains economically challenging. Launch costs need to drop substantially, and questions about microwave transmission safety and efficiency need resolution. But if achieved, space solar could provide clean baseload power without the land use and intermittency issues of terrestrial solar. Asteroid mining could supply Earth with water, metals, and other resources without the environmental destruction of terrestrial mining. Some asteroids contain more platinum group metals than have ever been mined on Earth. Water from asteroids could support space-based manufacturing and fuel depots, but the economics depend on drastically cheaper space access, and if agriculture could provide protein without the land, water, and emissions footprints of livestock. This doesn't necessarily mean eliminating conventional agriculture, but it diversifies protein sources and reduces pressure on ecosystems. Plastic-eating bacteria and enzymes offer potential solutions to waste accumulation. Several organisms have been discovered or engineered that can break down plastics that normally persist for centuries. If these can be deployed at scale, they might help remediate plastic pollution in oceans and landfills. The challenges are ensuring they only target waste plastics and don't damage useful plastic products, and scaling biological processes to handle the billions of tons of plastic already in the environment. Gene drives could potentially eliminate invasive species or disease vectors like mosquitoes carrying malaria. A gene drive is a genetic modification that spreads rapidly through populations, overriding normal inheritance patterns. Release modified mosquitoes with a gene drive that reduces female fertility, and within generations, the population crashes. This has been proposed for malaria eradication, which kills hundreds of thousands annually, mostly children in Africa. But gene drives are essentially irreversible and could have unforeseen ecological effects. Eliminating one mosquito species might allow another to fill the niche, potentially carrying different diseases. And there's no way to restrict a gene drive to one geographic region. It could spread globally. The ethics are complex, weighing immediate human lives against long-term ecological risks. Advanced nuclear reactor designs promise safer, more efficient nuclear power with less long-lived waste. Molten salt reactors operate at lower pressures and can't melt down the way conventional reactors can. Traveling wave reactors could theoretically run on depleted uranium, consuming existing nuclear waste as fuel. Small modular reactors can be manufactured in factories and various other fields. This meta-innovation, using AI to accelerate innovation, could compound progress across all technical domains. But it also raises questions about scientific validation and understanding. If AI suggests solutions that work, but that humans don't fully understand, do we trust them? If AI-designed drugs cure diseases, but we can't explain the mechanism, do we use them? These aren't hypothetical questions. They're emerging now. Vertical farming and controlled environment agriculture could decouple food production from outdoor climate. Multi-story facilities growing crops hydroponically under LED lighting produce yields per acre far exceeding conventional farming. Use a fraction of the water, require no pesticides, and operate year-round regardless of weather. The challenge is energy cost for lighting and climate control. But as renewable energy becomes cheaper, vertical farming becomes more viable. These systems won't replace all agriculture. Growing wheat, corn, or rice vertically isn't economically feasible with current technology. But for high-value crops like leafy greens, herbs, and vegetables, vertical farming is already competitive in some markets. It provides resilience, continuing food production even when outdoor agriculture struggles with drought or extreme weather. Atmospheric water harvesting extracts moisture directly from air, producing fresh water anywhere humidity exists. Current systems work, but are energy intensive, requiring several kilowatt hours per litre. Research into more efficient materials and processes could reduce energy requirements substantially. Combined with solar power, atmospheric water harvesting could provide decentralized water security without depending on rainfall or existing water sources. Advanced materials are enabling capabilities that seemed impossible decades ago. Graphene, a single layer of carbon atoms, is stronger than steel, conducts electricity better than copper, and is nearly transparent. While large-scale production remains challenging, simpler solutions emerge. None of these technologies are magic bullets that solve everything. They're tools, each with particular applications, limitations, and trade-offs. The path forward isn't choosing one perfect solution, but deploying portfolios of innovations appropriate to specific contexts, constantly adapting as conditions change and our understanding improves. Innovation at the edge of possibility is how humanity expands what's achievable when conventional approaches reach their limits. Psychology and culture might seem abstract, abstract compared to technology and infrastructure, but they're actually foundational to how humanity navigates extreme futures. The most sophisticated climate models and technological innovations are meaningless if people can't psychologically cope with rapid change. If cultures fragment under stress, or if societies lose shared purpose and direction. Mental health, cultural adaptation, and collective meaning-making determine whether transitions are managed or chaotic. Mental health challenges are escalating under conditions of rapid change and uncertainty. Rates of anxiety and depression have increased substantially in recent decades, particularly among younger populations. A significant portion of young adults now report persistent anxiety about climate change, economic futures, and social instability. This isn't irrational anxiety disorder. It's proportionate response to genuine threats. The clinical question becomes how to maintain functionality and well-being while acknowledging real dangers. Traditional mental health approaches focus on treating individuals. Therapy helps people develop coping mechanisms. Medications can alleviate symptoms. Mindfulness practices reduce stress. These remain valuable. But when distress is a reasonable response to genuinely and sense of belonging to communities, whether stress better than isolated individuals. Yet modern life, particularly in wealthy urban environments, often undermines social connection. People move frequently for work, living far from extended family. Neighborhoods lack shared spaces where casual interaction occurs naturally. Social media creates illusion of connection, while actual face-to-face interaction declines. Research from disaster psychology shows that communities with strong pre-existing social ties recover faster from crises than fragmented communities. When hurricane or earthquake strikes, neighborhoods where people know each other coordinate mutual aid, share resources, and provide emotional support. Communities where people are strangers struggle more, with everyone facing crisis individually. Building community resilience requires intentional effort. Creating and maintaining shared spaces, parks, community centres, libraries where people gather casually. Supporting local institutions, neighbourhood associations, cultural organisations, religious groups that provide ongoing connection. Designing cities for walkability and interaction, rather than isolation in cars and private homes. These aren't luxuries, they're infrastructure for psychological and social resilience. Cultural preservation faces tension with adaptation during rapid change. Traditional cultures, languages, practices and identities developed over centuries in specific environmental and social contexts
When those contexts shift rapidly, cultures must either adapt or risk becoming irrelevant to members facing new realities. This creates pain, particularly for older generations who see traditions fading. But culture has always evolved. Languages absorb new words. Practices adapt to new technologies. Values shift across generations. The question isn't whether culture changes. It's whether change happens through voluntary evolution that maintains cultural identity and continuity, or through coercive display. Under rapid change, older generations formed identities and values in different contexts. They often struggle to understand why younger people don't share their priorities or assumptions. Younger generations, facing radically different futures than their elders experienced, often feel betrayed, inheriting problems they didn't create but must solve. Climate change exemplifies this. People born before 1970 grew up assuming stable climate. They made decisions about careers, housing, family planning, without factoring climate disruption. People born after 1990 have never known climate stability. They face futures of increasing extreme weather, migration pressure, and ecological disruption, while often blamed for being too pessimistic or not working hard enough. These generational tensions aren't just personal, they're political. Climate action requires current sacrifice for future benefit. Older voters with shorter time horizons might resist policies they'll partly pay for, but mostly won't live to fully benefit from. Younger voters demand action on problems disproportionately affecting them, but often lack political power to force it. Bridging generational divides requires empathy in both directions. Older generations, acknowledging that they benefited from conditions that created problems younger people inherit. Younger generations, recognizing that older people face their own anxieties about rapid change, undermining the world they understand. Neither generation chose these circumstances, but both must navigate them. Education systems need radical restructuring for high uncertainty futures. Current models train students for specific careers expected to last decades. Students spend years mastering knowledge and skills that might be obsolete before careers end. This made sense when the world changed slowly. It's maladaptive when change accelerates. Future-oriented education focuses less on memorizing facts or procedures and more on meta skills. Learning how to learn, critical thinking, adaptability, collaboration, understanding underlying principles rather than specific applications. Adults, financial support during retraining periods, social acceptance that career transitions are normal rather than signs of failure. The role of narrative and shared purpose becomes critical during turbulent transitions. Societies need stories that make sense of change and provide direction. These narratives don't have to be true in a factual sense. They need to be true in a psychological sense, providing meaning, purpose, and framework for understanding experience. The post-World War II era had powerful narratives in many societies. Economic development and rising living standards, scientific progress solving problems,
expansion of rights and opportunities. These narratives weren't entirely accurate. They ignored inequality, environmental damage, and various injustices. But they provided shared sense of direction and progress that helped societies navigate transitions. Those narratives are breaking down. Economic growth is slowing and benefits concentrating. Scientific progress creates as many problems as it solves. Expansion of some rights faces backlash. Climate change undermines progress. Narratives we're moving toward worse conditions rather than better. New narratives haven't coalesced yet, creating vacuum. Different groups propose competing narratives. Some call for a return to imagined past stability. Others embrace radical transformation toward utopian futures. Still, others advocate pragmatic adaptation, focused on resilience over progress. Which narratives gain traction will partly determine how societies organize themselves and what futures they create. Philosophical and spiritual frameworks help individuals navigate uncertainty and maintain meaning beyond material circumstances. Religious traditions offer time-tested approaches to purpose, mortality, suffering, and ethical living. They provide community, ritual, and transcendent meaning that can sustain people through difficult transitions. Secular philosophies offer alternatives. Stoicism teaches accepting what you can't control, while focusing energy on what you can influence. Existentialism emphasizes creating personal meaning through choices. Survive. But humanity as species persisted. Cultures evolved, knowledge accumulated, and often people's lives eventually improved. This doesn't guarantee similar outcomes from current challenges. Scale and speed of change might exceed historical precedents in ways that break systems more completely. But it demonstrates human capacity for adaptation, resilience, and rebuilding. That capacity is psychological and cultural as much as technological. The critical difference between managed transition and chaotic collapse often comes down to psychological factors. Whether people maintain hope and agency or fall into paralysis and despair. Whether communities cooperate or fragment into competing groups. Whether cultural narratives provide direction or break down into confusion. Whether individuals find meaning and purpose or lose sense of why effort matters. Technology can provide tools. Policy can shape incentives. But human psychology and culture determine whether people use tools effectively, support necessary policies, and maintain effort through difficult transitions. The extreme futures we're facing require not just technological innovation and institutional reform, but also psychological resilience and cultural adaptation that help people maintain functionality and meaning while everything changes around them. This is perhaps the hardest challenge because it's the least amenable to simple solutions. You can deploy a technology relatively quickly. You can change a policy with legislation, but you can't easily repair fragmented communities, restore cultural continuity, or create shared purpose. These require patient, sustained effort, building social capital and meaning-making capacity that modern efficiency-focused systems tend to undervalue. Yet without them, even the best technology and policy often fail because people lack psychological and social capacity to implement them. Scenarios, cooperation, each of which faces significant obstacles. Renewable energy is economically competitive, but requires massive infrastructure investment and grid modernization. Nuclear power offers baseload, clean energy, but faces public resistance and regulatory complexity. Carbon capture could provide backup options, but remains expensive and unproven at scale. The optimistic climate scenario involves rapid deployment of existing technologies, breakthrough innovations that accelerate decarbonization, successful international coordination through mechanisms like carbon pricing or technology transfer, and societal acceptance of necessary changes in consumption and land use. This is achievable with current knowledge and technology. It requires political will and sustained effort more than miraculous inventions. The pessimistic scenario involves continued fossil fuel use due to political resistance, economic lock-in, or international cooperation failures. Climate impacts intensify, creating cascading crises that absorb resources and attention that could otherwise go toward mitigation. Tipping points cascade, amplifying warming beyond what emissions alone would cause. Adaptation becomes overwhelmingly difficult as multiple systems fail simultaneously. Between these extremes lie mixed scenarios, where some regions and sectors decarbonize while others don't, where partial action reduces warming but not enough to avoid significant impacts, where adaptation succeeds in wealthy regions but fails elsewhere. These middle paths are perhaps most likely, reflecting the messy reality of incomplete cooperation and uneven progress. Technology futures similarly branch. The AI development trajectory could lead to broadly beneficial augmentation of human capabilities, catastrophic accidents from inadequately controlled powerful systems, or concentrated power where a few entities control transformative capabilities. Which path we follow depends partly on technical choices about AI safety and alignment, partly on governance decisions about regulation and access, and partly on societal choices about what applications we pursue and permit. The optimistic AI scenario involves systems that enhance human creativity and problem-solving without replacing human judgment in critical domains. AI accelerates scientific discovery. Technology succeeds technically, but fails socially. Mixed scenarios involve AI delivering substantial benefits in some domains, while creating serious problems in others. Medical AI improves healthcare, while labor market disruption creates unemployment. Educational AI personalizes learning, while exacerbating inequality between those with access and those without. The outcome is neither utopian nor catastrophic, but messy and contested. Biotechnology futures branch similarly. Gene editing could eliminate genetic diseases, enhance crops to withstand climate stress, and create beneficial organisms. Or it could create unforeseen ecological problems through released engineered organisms. Exacerbate inequality through expensive enhancements available only to the wealthy. or enable bioweapons through accessible gene synthesis technology. Governance choices about regulation, access, and applications determine outcomes. Geopolitical futures range from renewed cooperation on global challenges to fragmentation into competing blocs to outright conflict. The difference matters enormously for addressing climate, managing technology development, handling migration, and maintaining trade that enables economic development. Cooperation allows burden sharing and coordinated action. Fragmentation makes everything harder, requiring each nation or bloc to solve problems independently while competing for resources and advantage. Space futures could see humanity expanding beyond Earth through Mars colonization, asteroid mining, and orbital manufacturing, creating new economic opportunities and insurance against planetary catastrophe. Or space could remain marginal, with occasional missions but no significant off-world presence, making humanity permanently dependent on one fragile planet. The difference is determined by technology costs, political commitment, and whether economic cases for space development materialize. Personal resilience strategies vary depending on which futures seem most likely and which capabilities prove most valuable. If climate disruption dominates, skills in agriculture, water management, infrastructure repair, and community organizing become critical. If technological unemployment dominates, creative skills, social intelligence, and adaptability become paramount.
Geographies and currencies hedges against various economic scenarios. Avoiding excessive debt provides flexibility. Maintaining some liquid assets enables responding to opportunities or emergencies. But in extreme scenarios, financial wealth matters less than physical capability, social connections, and access to essential resources. Collective action requirements exceed what individuals can achieve alone. Climate stabilization requires policy changes at national and international levels. Technology governance requires regulatory frameworks that don't yet exist. Social safety nets for displaced workers require political will to tax and spend on programs that benefit others. Infrastructure resilience requires public investment. None of these happen through individual choice alone. This creates an agency paradox. Individuals can control their own preparations, but outcomes depend on collective action that individuals can only influence marginally. You can build personal resilience, but if society fragments and systems collapse, personal preparations provide limited protection. You can advocate for policy changes, but your individual voice barely registers in mass democracies. The temptation is either paralysis, why act when individual actions don't matter, or retreat into purely personal preparation while ignoring collective challenges. The resolution is recognizing that collective action emerges from aggregated individual actions. Social movements build from individual participation. Policy changes result from accumulated pressure by many individuals. Cultural norms shift through countless individual choices. Your individual contribution is small, but not meaningless. And more important, acting provides agency and purpose, even when outcomes remain uncertain. The role of hope and agency versus paralysis and denial shapes outcomes profoundly. Realistic pessimism that acknowledges dangers can motivate action if combined with belief that action matters. But excessive pessimism leads to paralysis. Why act if everything's doomed? Unrealistic optimism that downplays dangers leads to complacency. The psychological sweet spot is realistic assessment of threats, combined with belief in human agency to shape outcomes.
Hope is not the same as confidence. Confidence implies certainty about positive outcomes. Hope recognizes uncertainty but chooses resources.
Economic collapses or breakthroughs could redistribute power and possibility. Black swan events, by definition, can't be predicted, but will almost certainly occur. This irreducible uncertainty means preparation can't be optimization for predicted futures. It must be building capacity to adapt to unpredicted futures. Resilience over efficiency. Flexibility over specialization. Multiple strategies over single solutions. This is harder psychologically than having clear plans, but more realistic given genuine uncertainty about which challenges will prove most important. The difference between adapting to change and shaping change matters morally, even if outcomes are similar. Passive adaptation means accepting whatever future emerges from accumulated impacts and others' choices. Active shaping means intentionally working toward preferred futures, even if success isn't guaranteed. The outcome might look similar, but the process of choosing and acting matters for human dignity and agency. We're preparing for futures plural, not one predetermined future. Climate scenarios, technology trajectories, geopolitical configurations, all branch based on choices accumulating now. Some choices are individual. What skills to develop, what communities to build, how to live. Others are collective. What policies to support, what technologies to develop, what values to prioritize. Both matter. The branching paths aren't equally likely. Some futures are more probable than others based on current trends, institutional inertia, and political realities. But probability isn't destiny. Unlikely futures become reality when enough people work toward them consistently. The clean energy transition seemed impossible until it started happening. Societal changes that seemed unthinkable become normal within a generation when enough people push for them. We're living in the branching point. The decisions made in the next few years determine which branches remain accessible and which close off. Climate tipping points, once crossed, can't be reversed on relevant timescales. Technology trajectories, once established, create path dependencies difficult to shift. Black swan events. In the landscape of coming decades, living with, not eliminating, uncertainty becomes both a practical and philosophical imperative. No amount of data or modeling lets us predict which scenario, optimistic, pessimistic, or something between, will actually unfold. History is full of turning points brought about not by linear trends, but by unexpected shocks. Pandemics, technological leaps, wars, social movements, and natural disasters that completely upend established paths. Black swans, by definition, are beyond anticipation, yet their cumulative effects shape the world more than any single predictable trend. This means we must rethink the logic of preparedness. Traditional approaches focus on optimizing for what is most probable, but extreme futures demand anti-fragility, the ability to gain from disorder and adapt under stress, rather than simply survive until order is restored. Anti-fragile systems go beyond resilience. They reconfigure, improve, or innovate in crises.
Consider how the global response to COVID-19 produced previously unimaginable advances in vaccine technology in record time, or how digital platforms scaled rapidly when in-person alternatives vanished. Diverse strategies are essential. The most robust organizations, communities, and individuals avoid betting everything on one vision of the future. Instead, they diversify investments, skills, and approaches, maintaining the ability to pivot. Polycultures in agriculture withstand pests and climate swings better than monocultures. Mixed urban-rural infrastructure provides backup when one mode of living faces disruption. At a personal level, portfolio careers and lifelong learning are more future-proof than single specialization trajectories. Yet not all uncertainties can be managed individually. Some can only be addressed collectively. Through robust governance, adaptable social safety nets, investment in public goods, and ongoing stewardship of the ethical frameworks, and kindled global solidarity in unexpected ways. Our challenge is not to eliminate uncertainty, but to cultivate curiosity, adaptability, and compassion within its shadow. To build systems, educational, economic, technological, that are less brittle when tested. To prize diversity in thinking, in resources, in culture, over rigidity and uniformity. To hold hope, not as denial of risk, but as a commitment to shaping possibility, even when the outcome is unknown. We end not with neat conclusions, but with open questions. How can we prepare minds and hearts for futures we cannot imagine in detail? What skills and values help us not only endure, but flourish in constant flux? How can societies maintain cohesion and fairness amid instability? What stories will we tell about this transition? And what lessons will be drawn? Preparation for extreme futures is not about predicting a single arrival. It's about learning to live with and shape the many possible worlds moving toward us. The ultimate tools are human: adaptability, imagination, solidarity, and the ever-renewable capacity to find renewal in uncertainty. That, more than any particular plan or forecast, is what will carry us through humanity's next chapter.